Okay, welcome to research methods. Today we're talking about statistics again, but this time we're talking about what are called inferential statistics. We talked about descriptive statistics last time. Okay, so what are inferential statistics? Inferential statistics, it says there, are methods that use the results obtained from samples to help make generalizations about populations. What that really means is that basically these are methods where you compare your sample, the data, the results you get from your sample to your population. So you want to determine, for instance, say a little bit more, you want to determine if there's a difference, let's say, between males and females, let's say, and say how much they drink alcohol. And you found a certain result from your sample, a certain difference, let's say, and you want to determine if that actually exists in the population. That's what you do with inferential statistics. You basically are going to infer something from your data. Is there a difference? Is there an effect? Does this treatment work? Does this drug work? And you want to say that your sample basically says something about the population. You don't want to say that your sample, you don't want to say that your results actually are due to nothing more than what is called sampling error. Sampling error is a naturally occurring difference between the sample statistic and the corresponding population. So if you find a certain result, you find a certain difference, let's say, between men and women in how much they drink, if your results are due to sampling error, that means there's no real difference there, okay? That it's just a random difference. It's just by chance that you found this difference, and it doesn't really say something about the population. That's kind of what we mean by inferential statistics, okay? So it's a little bit more than what you do with descriptive statistics. You're not just describing what you found, you are trying to determine something from your data. You're trying to basically infer something. You're trying to reach some conclusion that there's some difference, some effect, something like that. Okay, it's a little bit more complicated, but not that much more complicated. It just sounds a lot more complicated. When I show you how to actually do this with actual data, you'll see it's not that bad. A little bit more complicated, but not that much. Here's an example. Some information here about a population. So the big oval at the top, information about a population. So let's say there's a population of 1,000 college students. That's how many college students that say they're at a certain college, okay? I guess that would be kind of small, okay? Ours is like 15,000, okay? But that's the population, 1,000 college students. And then we have the population parameters, which, remember, parameters are just like statistics, but except they refer to the population. So the average age of those college students is 21.3 years, okay? The average IQ is about 112.5. Yes, college students should be smarter than average, okay? There are those in college after all. A lot that are not as smart, right? Less than average, probably wouldn't go to college. So the average IQ is about 112.5. About 56% female, 44% male. Okay, yes, we are finding that more females are attending college now than males. So that's the population. That's what describes the population. You can take a sample from that population. You can, let's say, select a certain group of people that you study that, let's say, form part of your survey. That maybe sample one. Let's say you select Eric, David, Laura, Karen, and Brian. Let's just say 5 of them, okay? And you find, so the sample one, okay, you find that their average, so that would be the sample statistics. Statistics refer to samples, okay? So the average age for those that you selected, those that, let's say, are in your survey, I know you would have more than 5, but this is just an example. The average age is 19.6. The average IQ is 104.6. 40% female, 60% male. So you can see that there's some slight differences between your sample and the population. Let's say you select another sample. Okay, sample 2. This time you select Stacy, Kirsten, Sarah, Andrew, and Jessica. All right. The average age of these is 20.4. The average IQ is about 114.2, about 80% female, 20% male. Still, there are some differences. There's always going to be some slight differences between your population and your sample, okay? And those differences are often due to what we call sampling error. They're just different because you don't have everybody in the population. So your statistics for your sample are not going to be the same as, say, your parameters for the population. So that's what we call sampling error. Just by the very fact that you have different people, and not everybody, right? You only have some, there's gonna be differences, okay? And those differences are just due to chance, just due to luck, right? Those differences don't really matter. We call that sampling error. That error actually makes it more difficult for us to actually find any effects, find any differences, when we test things. So just an illustration there. Here's an example for you guys. An example of an experiment. And we'll talk about experiments after the second exam in more detail. But let's say you want to determine if there's a relationship between TV violence and aggression, okay? So you have a sample of kids, let's say, watch TV violence for 30 minutes. Some children, right? They watch a violent TV show for about 30 minutes. Another sample of kids, they watch a non-violent TV show for about 30 minutes. So one watches violent TV, the other one watches non-violent TV. You have two different samples. Now here's the thing, those samples are gonna differ on their own without it having anything to do with the TV. They're gonna be different on their own because they're different kids. So that naturally occurring difference is called sampling error. What you want to know is, beyond that, is there any difference that's due to watching violent TV, for instance? So the researcher will observe, right? Will record the aggressive behavior, right? And let's say the results show that there's a 4-point difference between these conditions. There's a 4-point difference, let's say, in aggression between those that watch violent TV and those that watch non-violent TV, okay? What you want to determine is this result, this 4-point difference, is it due to the treatments, okay? Is it due to the different TV programs? Is it a real difference, in other words, a real difference due to what you subjected these kids to, right? Or is it simply due to sampling error? Do you find that difference simply because there's different kids and they happen to be different and it has nothing to do with the violent TV, okay? So in other words, does TV violence have an effect on aggression, or is it the result of chance? Okay, of course you want to find that TV violence does have an effect on aggression, right? If you're trying to publish something and you're testing something, you want to determine that there's an effect there. But it could be that what you find is nothing more than error, sampling error. It's nothing more than chance or luck. There's no real difference, and it's therefore not worth publishing. Okay, so that's just an example. Here's visually what it looks like. The population of preschool children, okay? Sample 1, which was assigned to treatment A, the nonviolent TV, their measure of aggression was 3.4. And sample 2, which was assigned to watch violent TV, which are different kids, their average aggression, mean aggression there is 7.6. So you can see there's a little bit more than a 4-point difference, 4.2, okay? Is that difference a real difference due to the violent TV, right? Or is it a difference that's due to chance, due to luck, due to sampling error, due to the fact that the children differ already on their own? It's unlikely that these children are going to be exactly the same. They're different children in these different groups. So let's talk more about this, the way this actually works. Okay, so with inferential statistics, once you collect the data, right? And of course, you enter it into a statistical software program. We don't calculate things by hand anymore. We don't do it on paper and pencil. It's all done by computers. Okay, so once the data is collected, you enter into the software program. It is time to test the hypothesis. Inferential statistics involves hypothesis testing. Okay, that is what it's really about. I should have told you guys. I told you guys about testing an effect, finding some difference. The way we do that is with a hypothesis test, okay? So remember, the research results come from the sample, okay? Not from the population. Your results come from the sample. Certain sample of people participate in your survey, in your experiment, whatever it is, right? The results come from the sample. So you need to evaluate whether you can make a general conclusion from the sample about the population. You need to determine whether what you found from the sample says something about the population, or whether your sample, or whether your finding is just error, basically, sampling error. That's what you're trying to determine. In other words, what you found, is it real or is it not real? Okay, if it's real, that means it really refers to what's happening in the population. If it's not real, it's just due to error, sampling error. Okay, more about this. So with a hypothesis test, And if the word hypothesis test confuses you, right, it sounds complicated, just think of it as a test, okay? You're gonna test the difference, okay, among groups, let's say. So a hypothesis test uses sample data, right? It uses data, right, to evaluate the credibility of a hypothesis about the population. A hypothesis test tries to determine whether the difference you found or what you find says something about the population. That's really what that means. So a hypothesis test distinguishes among two possibilities, all right, two possible explanations. There's two possibilities when you do this test. One possibility is that the data were produced by random variation from chance or sampling error. So one possibility is that whatever your result is, it's just due to sampling error. That would mean that your findings, your data, are due to chance, and that what you're really doing is you're finding evidence for the null hypothesis. The null hypothesis is supported. The null hypothesis simply says that there is no real difference, that what you found is due to chance. That's the null hypothesis. It says there's nothing happening here, nothing interesting. This is just random variation, okay? So your result, your hypothesis might show that. It might show evidence for the null hypothesis. Another possibility, which is the one you want, is that the data represents systematic relationships among variables in the population. What that means is that your data shows a real difference, a real effect. So your findings, your data, accurately represent the population, the alternative hypothesis, that your data accurately show that there is a difference, that there is some effect. That's the alternative hypothesis. The alternative hypothesis says that there is some real difference, that what you found is real. It's a real difference. It's really what's happening in the population. That's what it means, okay? So two possibilities of the hypothesis test. It shows that there's no significant finding here, that it's all due to error, right? Your result is due to error, or that there is a real finding here, right? That there is something real, something that represents the population. That's really what it's saying. Like I told you guys, it gets a little bit philosophical as to what it means. But what it's really saying is something simple. There's either a real difference or there isn't a real difference. That's what a hypothesis test tells you. And we're going to talk about how it does that. So remember, with a hypothesis test, the null hypothesis states that there is no effect, right? No change. Any pattern that you find is due to chance. So if you find a difference between men and women, a difference in aggression in children, let's say whatever it is, that effect isn't real. It isn't statistically significant. That's another way of putting it, right? That is something that's due to chance. That's due to luck. It's due to sampling error. That's what the null hypothesis says. Null means basically void, nothing, right? The null hypothesis says that there's nothing. So the null hypothesis really says there is no difference. There's no effect. That's what the null hypothesis says. The example here, the example about the study evaluating the effect of TV violence and aggression. The null hypothesis says that there is no difference in aggression between those that watch violent TV and those that watch non-violent TV. That's what the null hypothesis says. It says there's no difference between those children that watch violent and non-violent TV. It says that the mean difference between the treatments is 0, right? It says that basically your difference between the averages in aggression of the two populations of kids, the two samples of kids, is 0. Maybe it's not 0, maybe it's not exactly 0, but it's pretty damn close to 0. It might as well be 0. It says there's no difference, okay? Any difference that you found, right, is non-significant and due to chance or sampling error. If there is a difference, if it's not exactly 0, if there is a difference, that difference, what it means is that difference is usually not significant. It's probably small, and it really says that there is no difference there, and that small difference is actually due to sampling error. It's just due to chance or luck. In other words, there's no effect, okay? That's what the null hypothesis says. Because you could find a difference between the treatments, right, between the different conditions, but that difference might be so small it doesn't matter. And we'll find out in a moment how we know if the difference is big enough to matter, or if it's not big enough and it's just basically means that there's nothing there. There's no difference. In other words, that the null hypothesis is supported. A little bit here about how the math works, okay? But I'm not really using any math here. I'm just explaining it without the math. So the test statistic, the hypothesis test, what it actually tests, what it looks for, is that what it compares is that it compares the actual difference between the data and what the null hypothesis says. Okay, that difference divided by the difference you expect by chance. So let's say that you found a difference in the data, right? A difference of, let's say, 1, okay? The null hypothesis predicts that, you know, there would be a 0 difference, okay? That's what the null hypothesis says. So the difference there, right? 1 minus 0, well, 1, okay? That's what's in the numerator. The difference expected by chance, let's say by chance you expect about a 1. Okay, 1 divided by 1 gives you 1. Okay, so if the test statistic, if it equals to a value near 1, that means your results represent nothing more than chance. That means that what you found and what's expected by chance is pretty much the same. So in other words, it's chance, okay? There's no treatment effect. There's no difference, okay? The results are consistent with the null hypothesis. You do not reject the null hypothesis. It is consistent with the null hypothesis. There is no difference. Okay, null hypothesis is not rejected. This test statistic, by the way, could be a T, it could be a T test, it could be an F test. There's many different kinds of tests. But what it's actually doing, it's comparing what you found, you know, with the null hypothesis, and basically dividing that by what's expected by chance. It's doing something like that. The equation is usually more complicated, but that's the logic of it. It's comparing what you found versus, you know, what you expect by chance. The null hypothesis always says that there is no difference. Now, you could have a different outcome. The test statistic, remember, represents the difference that you found, right? Minus the null hypothesis and the difference expected by chance, okay? If the test statistic, if the number that you find when you do that math, right? And remember, in real life, the equation could be more complicated. This is just representing the logic. If the test statistic has a value much greater than 1, okay? That means that there is a real difference, okay? That the treatment effect is real, okay? So in other words, let's say you found a difference of, let's say, 3. The null hypothesis predicts 0, okay? The difference you expect by chance, let's say, is 1, right? 3 divided by 1 is 3. That number is much bigger than 1, right? So the test statistic is bigger than 1. That means there's a real difference there. You found something bigger than what is expected by chance. There's a real difference, okay? The actual results should be bigger than expected by chance, okay? They are. There's a large difference between the data, what the data suggests, and the null hypothesis. And remember, the null hypothesis says there is no difference. And you found something that's different than the null hypothesis. So in this case, you reject the null hypothesis. In other words, the finding that says, the prediction that says there's no difference, you reject that. And instead you say there is a real difference. That's the way the logic works, okay? So you test something. One outcome is that there's no difference. Another outcome is that there is a difference. And your goal is to reject basically the prediction that says there's no difference. You want to reject that one, and you want to say the evidence doesn't support that prediction. It supports the other one that says there's a difference. That's the logic behind this. Let's keep going. This is gonna make it sound like it's a little bit more complicated, but it's actually not that complicated, okay? You need to determine whether the difference that you found is actually significant, if it's real, right? So you need to be concerned with something called the alpha level, the levels of significance. Because the T statistic is gonna give you one thing, okay? But you also need something else to determine if the difference is actually real. First of all, you have your alpha level. That's the level of significance that you are, that you're hoping for, the alpha level, okay? So the alpha level is the maximum probability that the sample results are due to chance, that the null hypothesis is true. The alpha level represents, or you can just call it the alpha, it represents the chance that, that the difference is not real, okay? The chance that the null hypothesis is true. We usually want our alpha levels to be small. 0.05 means that there's only a 5% chance that the null hypothesis is true. Okay, if there's a 5% chance that there's no difference, that means there's a 95% chance that there is a difference. Okay, and that's usually what you usually choose as your alpha level. For psychology, we want no bigger than a 5% chance that the results basically support the null hypothesis. So our alpha level is usually set to 0.05. Okay. There's no more than a 5% chance the results are due to error, to sampling error, or to chance. Other alpha level, 0.01, that means there's only a 1% chance that the results are due to chance, right? 1% chance that the null hypothesis is supported, right? 0.001 means that there's a 0.1% chance, right? It's 0.1% is what that means, that the results support the null hypothesis, okay? So for significance to be achieved, right, you need your alpha level set at 0.05 or less, okay? You want no more than a 5% chance that the null hypothesis is true, because you found your result. Let's say you find your result, right? Or, you know, if it's more than 0.05, that means there's more than a 5% chance that it's due to error, and that's too much. That's the maximum that we allow. You could get close to it, right? And then you have to determine whether this is acceptable or not. But just so you're not confused, because we're going to talk about p-values in a little bit, the alpha level usually refers to your prediction, okay? You are predicting that you're going to find a real difference, and the results of that difference is not true, that it's due to chance, is 5% or less. The alpha level has to do with your prediction, okay? Because you're going to compare your alpha level to what's called the p-value, okay? We compare the alpha level, which is our prediction, with the p-value. The p-value, okay, so the p-value, just to tell you guys right off the bat, the p-value refers to your result, okay? It's basically the probability that your result, what you actually found, is due to error or chance, okay? So we compare the alpha level with the p-value to determine whether the observed data are statistically significant from the null hypothesis. So if the p-value is less than or equal to the alpha level, that means we reject the null hypothesis, and we say the result is statistically significant. Let me explain what that means, okay? So you're predicting that there's going to be a real difference, okay? And you set your alpha at 0.05. You're predicting the differences that you found, that you're going to find, let's say, because remember, first you have a prediction, right? You have a hypothesis. You predict that you're going to find a real difference, and that basically your, that the chance that difference isn't real is 5%. Okay, that's your alpha. That's your prediction. Now, when you actually get your result, you do that hypothesis test. It tells you that your p-value, let's say, is 0.01. So your result is telling you there's a 1% chance that this result is due to error. 1% chance that this difference isn't real. Okay, so you were predicting at least 5%. You got 1%, which is even better. Okay, that means your p-value is less than alpha, less than the maximum error that you're willing to tolerate. So what you found is less than what you're willing to tolerate, right? Therefore, you reject the null hypothesis. So put it this way: you wanted there to be no more than a 5% chance that your result isn't real. That's your alpha, 0.05, right? And what you found with your p-value, let's say, is that it's 0.01. You found that there's a 1% chance that your difference isn't real. 1% is even better than 5%. So that means that, yes, okay, this is a real difference. You reject the null hypothesis. Okay, to make it simple, I just want to tell you guys, your alpha level is always set at 0.05, okay? It's always 0.05. So whenever you look at your result, what you do is you only look at the p-value. You don't even worry about the alpha. You just look at your p-value. If it's 0.05 or less, it's significant. And some of you may remember when you took statistics and you let's say you used that statistics book and you were looking, remember, at the tables in the back, and you were looking for those numbers, you know, the value of the t-test, let's say, or some other test, and you were looking for basically the number said 0.05, 0.1, you know, 0.075, and you remember looking at stuff like that? You were looking there for the p-value is what you were doing. You don't need to do that, by the way. When you use software, it just spits it out, tells you the p-value. And if it's 0.05 or less, that means you have a real difference. The test statistic tells you basically, you know, what the value is, basically what the difference, you know, that you found compared to what's expected by chance. The p-value tells you if that difference is really real or not, or the chances that it is real or not. And you want no more than a 5% chance that it's not real. How do you report your results from the hypothesis test? So let's say your study finds that there's a difference between two treatments, right? Let's say that those that watch violent TV and those that watch non-violent TV, let's say you found a difference, right? And the computer reports a significant level of p equals 0.028. That's what the result is. The p-value is 0.028, right? Therefore, you reject the null hypothesis. Your p is less than your alpha. P 0.028 is less than 0.05. So you report results that your results are significant with your p-value less than 0.05. Or you can use p equals 0.028. You can write it that way and just give the exact value. If you find a non-significant result, then you report it as p greater than 0.05. So let's say you find that p was equal to 0.10, which means there's a 10% chance that the difference isn't real. That's too much, 10% chance that it's fake, basically, that it's an error. That's too much. So therefore, you say that the difference is not significant, and you put p greater than 0.05. Or nowadays, it's just more useful to just put p equals just 0.10 or 0.20, whatever you found, instead of just, you know, the greater or less than thing. It's better nowadays if we just report exact results, not greater or less than, because there's other people who are going to look at our results and they want to know exactly what we found so they can compare different studies. Okay. So for recent studies, you report, let's say p equals 0.028, basically. You report the exact number. And it's better if you do it that way. But if you do it this other way, where you just say p less than or p less than or greater than, then that's still okay. Some examples of hypothesis tests. So I told you the way it works, the logic behind it. That's what that was. It's kind of like the philosophy behind it, with a little bit of, not real math, but with a little bit of, at least conceptually how the math works, okay? So examples of hypothesis tests. One example is what's called a test for mean differences. When you talk about statistics, it always sounds complicated, and often it doesn't really mean something that complicated. Test for mean differences. So you can basically test the difference between groups. That's what that means. So let's say you want to compare the average difference between group A and group B. That's a mean difference. Remember, mean means average. Average difference, right? You're going to test the average differences. The average difference for this group versus that group, right? One example of that is what's called a two-group between subjects test. So you're going to compare two groups, right? That's what that means. And between subjects means that you're using different participants for one group and the other, right? That the two groups, for instance, so it's two groups, and those two groups are made up of different people. That's what we mean by a two-group between subjects test. And what that is called, the test that you use for that, to test those two groups, it's called an independent measures t-test. You guys just know it as a t-test, but there's different kinds of t-tests. The independent measures t-test is the t-test that you use when your two groups are composed of different participants. Sometimes your two groups have the same participants, okay? And that would be a different kind of t-test. But I'll tell you guys about those groups when we talk about experiments, okay, after the second exam. But most experiments, or most of the time when you test differences between groups that are made of different people. So most of the time you use this independent measures t-test. But there are others, okay, that you might need to use if the groups are made of the same participants, okay? So you can compare different treatments, let's say, alcohol versus no alcohol. This group of people, let's say, consumed alcohol. This group of people did not. And we basically found their average level of aggression. You're going to compare the average level of aggression between the alcohol group and the no alcohol group. You use an independent measures t-test. The null hypothesis states that the mean difference is 0. The null hypothesis always says that there is no difference. Okay. I hope you guys are getting this. Like I said, it is kind of philosophical, right? It sounds complicated. It's not that complicated. You'll see when I show you guys how to do this with the real data. It's not hard. And by the way, all of you have to know about this stuff for the sake of the exam, right? It's going to be tested in the homework and the exam. When it comes to doing this, though, applying this, those of you who are doing an honors project are going to have to do something like this, okay? You're going to have to go beyond the descriptive stuff. You have to do hypothesis testing. Okay, but I'm showing you guys how to do it now, okay? I'm telling you, but I'm going to show you how to do it after the recording's over. So test for mean differences again. So you use an independent measures t-test to compare the two means, right? What that really means is to compare the two groups, because remember the two groups have different averages, okay? So the t statistic, right, because it's a t-test, the t is basically what we call it, right? The t equals something. The t statistic is an actual ratio that compares the actual difference with the expected difference if the null hypothesis were true. We talked about that already, right? That's what a hypothesis test does. A t-test is a type of hypothesis test. For instance, if t equals 3, that means the difference is 3 times larger than what would be expected if there was no difference. So, this is how you, you write the way you report the results. Test for mean differences, okay? So the results are reported in the following format. This is the way you report it. T, for instance, and then in parentheses, you have what are called your degrees of freedom, okay? And that equals 3, right? 3.00, comma, P equals 0.001. So let's say you did this t-test, right? And the t-test equals 3. That's the number that you got. Your p-value was 0.01. You should know right away when you look at 0.01 that is a real difference, okay? There's a 1% chance that that result isn't real, that it's due to error. 1% is less than 5%. So yes, you're going to reject the null hypothesis here. So what you report is t, and then the degrees of freedom in parentheses equals 3.00, comma, p equals 0.001. Note that the number in the parentheses is what we call the degrees of freedom. And the degrees of freedom is basically for a t-test is n minus 1, the sample size minus 1. So in other words, this result here was found with a sample of 29 participants. 29 participants were used for this test. And basically, the 29 participants is the sample, that's n, so n is 29, minus 1 is 28. So t, and then the degrees of freedom in parentheses equals whatever you got, and then the p-value. That's the way you report it. I will tell you though that when we do this in Excel or we do this in Google Sheets, we're not gonna find the actual t-value. There is a way to do it, I believe. In Excel, I don't know if you can do it in Google Sheets. There's a way to do it, but what I'm going to show you is, is a little bit different. I'm going to show you basically, when I show you how to do it, it's just going to give us the p-value. So you're really just going to report the p-value. And we'll talk about how to write this up when we talk about, well, how you present your results. And that's the next chapter that we'll get into next week. Okay. So in Excel and Google Sheets, we're just going to find that p-value. And if it's less than 0.05, that means there's a real difference. We're not going to worry about what the t statistic is, the degrees of freedom, because, well, Excel is not really meant for doing statistics or these kind of statistics. Neither is Google Sheets. I believe there's a way to do it. I don't really know how. I was trained in something called SPSS, and that's probably what you would be using, when you go to graduate school or something like that. And when you use that, when you use a real statistical software program, then you'll see the whole thing, okay? But we don't have that here, by the way. at the college. We need a computer lab, right? And we need all the computers to have that program so I can show you exactly how it's done and show you exactly this. But at least we're talking about it. But what I'm going to show you is a little bit simpler, but it's still the same thing. It's just we don't get all the numbers. Okay, so that was hypothesis testing. Okay, that was inferential statistics. Now, it is possible that when you do your results, when you do your inferential statistics, it's possible that researchers can reach an incorrect conclusion because of the results of the sample. It's possible, for instance, that you get your result, you think it's significant, right? And in reality, your result isn't real, okay? So there are errors in hypothesis testing. And there's two kinds of errors, okay? There are what we call type 1 errors. Type 1 errors is where the sample data shows that there's a significant effect, that there's a significant difference, for instance, but there is no effect in the population. So let's say you find a difference in IQ between men and women, and you found, like many studies do, that men have a slightly higher IQ than women. Let's say you found that, okay? It's possible that in the population, there is no real difference. It's possible and very likely that men are not smarter than women. It might even be the reverse, okay? It could be that women are actually smarter than men. But you found that men have a slightly higher IQ than women, okay? It's possible that that difference, even though your p-value says is significant, it's still possible that it's not a real difference, okay? And there's many reasons for this, okay? It could be that the test is flawed and biased in favor of men, right? It could be that the instructions given to the women were a little bit more confusing. There's many different reasons why this could happen. But a type 1 error is when you find a significant difference. In other words, you found a real difference in your sample, in the people you tested, but there's no real difference in the population. It's not real. In the population, no such difference exists, okay? So what happened here is that the researcher may have selected an unusual or extreme sample. Maybe the people you selected, right, don't really represent what's happening in the population. Maybe you selected, for instance, men that are just a little bit more knowledgeable, let's say, than the women on average. In the population, let's say there's no such difference, but you selected your sample such that the men are basically a little bit more advanced than the women. So in other words, you found a difference in your data, okay, but there is no real difference out there. It's like, put it to this way, it's like, okay, so you selected men that were smarter on average than the women than the women that you tested, right? So you tested men and women, but it's just by chance that you ended up selecting men that are a little bit smarter than the women. It doesn't mean that men are actually smarter than women in real life, that difference exists in the population. It's just that's what you got for your sample. I'll give you another example. I could easily do a survey where I can find that that Donald Trump has an 80% approval rating. I can do a survey like that. I can I can do that, right? Or let's say, well, that's actually not a good example. Let me give you another example. Okay, so let's say I do a survey, and my survey asks one question only: are you voting for Donald Trump? Okay, you could say, yes or no. Okay, let's say. That's still not a good example. Okay, never mind the example. Okay, but I can show you the point about this is that I can produce a result that seems real based on the sample I select. If I want to show something, if I want to show that men are smarter than women, I can do that by choosing certain people from my sample. If I want to show that women are smarter than men, I can also do that. I can show, for instance, that that Republicans are more likely to vote for Donald Trump than Democrats. We know that that's a real difference, but I can show the opposite. I can show also that the Democrats are more likely to vote for Donald Trump than Republicans. How can that be when we know that isn't true, right? It depends on the sample you select. If you select a certain group of people in a biased way, you can really show anything, but it means you didn't do the study correctly. You have a biased sample. The sample is powerful. It's really what determines your outcome. And the people that you get determine what you find. This is considered a false report, right? It's indicated by the alpha level or the p-value. So yeah, the p-value can tell you that the difference is real, but it can still be a false report if you didn't do the study right, if it's a biased sample, for instance, or the test is biased or something like that. Okay, so I don't want to confuse you guys. Type 1 error simply means that basically that you found a significant effect, right, in your sample. You found a real difference, but there is no such difference in the population. That's a type 1 error. There's also a type 2 error, okay? A type 2 error is where your sample did not show a significant effect. You didn't find a difference. You didn't find a real difference, but there is a real difference in the population. So it's the opposite kind of error. You found no difference in your samples, right? In your sample, but there's a real difference in the population. So let's put it this way. Let's say you found, this time I'm going to give you an appropriate example about Donald Trump. Let's say you do a survey. Let's say you could do this with experiments, with surveys, but let's say you do a survey and you ask people how much they like Donald Trump on a scale of 1 to 5, right? And you compare Republicans and Democrats, okay? And you found that there is no difference between Republicans and Democrats in how much they like Donald Trump. That's what you found. You found that there's no difference, but there is a real difference in the population. We know damn well Republicans like Donald Trump more than Democrats. How is it that you found that there's no difference? That's called a type 2 error. That's when you don't find a difference, but there actually is a difference. Okay? So that's possible when maybe the effect size is small and the sample data does not reproduce it. Okay? So it's possible that maybe the difference is small, right? And it's hard to basically to find that difference. When there's a very small difference, it's really hard to find it. Okay, so let's say if the difference between like how much Republicans and Democrats like Donald Trump, let's say the difference is small, then it would be hard to find that that effect is real or significant. In reality though, the difference is large, okay? Big difference between how much Republicans like Donald Trump and how much Democrats hate Donald Trump, and how much Democrats like Donald Trump, okay? But if the difference is small, I'll give you an example of a small difference. There is a small difference, according to research results, between the IQ of men and women. There's a very small difference. It might be 2 or 3 points. That doesn't mean that men are smarter than women, by the way. It's just that, you know, the test could be biased. But that small difference may not be significant. It may not be big enough to matter. That's what we mean. The difference is probably small, you know, and it's hard to show that that difference is actually significant or important. So you might find a type 2 error. It just simply means that you didn't find a difference, but in fact, there is a difference in the population, okay? The researcher might abandon the project, right? Oh, I didn't get anything significant. I didn't show a real difference. I didn't reject a null hypothesis. This is not worth publishing. It basically says there's no difference. You don't publish things that basically say there's no difference. You don't produce a study that says that, you're not gonna publish a study that says basically that there's no difference in the amount of alcohol that men and women consume. That's not interesting, okay? Now, if you find that there is a difference between men and women in the amount of alcohol they consume, if you find, for instance, that men consume a lot more alcohol than women on average, then that is worth publishing. Probably not because it's already been published, but what I mean is that is a real difference. You don't report that there is no difference. You're not gonna publish a study that says, study shows that blah, 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 there's no difference in this group and that group. Like, so what? There's no difference. Maybe there is and you just didn't find it. Or maybe you did the damn thing wrong, okay? Any result that shows that the null hypothesis is true is usually not worth publishing. Your aim is to reject the null hypothesis. Your aim is to say that there is a real difference. And when you have a type 2 error, you didn't find a difference, but there is a real difference in the population. So your study doesn't show that difference, so you may abandon it, say, this stupid thing didn't work out. On to something else, right? Let me do something else, right? You may not publish the results. Or maybe the researcher repeats the study with a larger sample size, right? Let's do the study again. Let's have more participants this time and see if we can find a real difference. Or use some other little things to tweak the study, refine the study to increase your chances of finding a significant result, okay? So a type 2 error, basically, just to summarize, is when you don't find a real difference, but in fact, there is a real difference in the population. Factors that influence the outcome of the hypothesis test. So there are things that make it more or less likely that you are actually going to find a real difference when you do a hypothesis test. One, obviously, we already actually mentioned this, is the number of scores in the sample. It's the sample size. How many participants do you use? How many participants in your study, right? Differences obtained from a small sample of participants are unstable, less likely to be significant, okay? If you only have a few participants in your study, it's harder to find a significant difference, okay? It's a small sample size is not a good sample size, okay? It's just, it's not a good thing, okay? You're more likely to find a real result when you have more participants, which is why I tell you that there's a certain minimum that I want when you do your survey. Even though we're not really doing a hypothesis test, you guys are not required to do it unless you're doing an honors project, right? Some of you will have to do a hypothesis, and you can do a hypothesis test with your survey. You compare men and women, people of different ethnicity, you can compare people of different age, right? But if your sample size is too small, your chances of finding a real difference are basically not good, okay? So the more participants you have, the better, okay? Differences obtained from large samples, if you have more participants, those differences are more stable, right? In other words, you're more likely finding something that is really what's happening on average. And if there is a difference, and you find a difference, it's more likely to be significant. So what this says basically is that more participants is a good thing. You want more participants. The more participants you have, the more likely it is that if there is a real difference in the population, you're going to show it in your sample. Other things, the size of the variance. The variance, what the heck is that? Okay, that's something that you should have learned from statistics, but it says there at the bottom that the variance is related to the standard deviation. The standard deviation squared is equal to the variance. So here's a hint for you guys. Variance has to do with variability, okay? The standard deviation has to do with variability. So does the variance, okay? So this has to do with variability, okay? The difference obtained from a sample with high variance is less likely to be significant. If when you test, let's say your participants, the people who make up your sample, if their scores are all over the place, a lot of variation in their scores, you are less likely to find a real difference among your groups. There's a lot of variation in the scores. It's kind of messy. They're all over the place. Okay, it's harder to find a difference that way. The difference obtained from a sample with low variance is more likely to be significant. If the scores are a little bit more restricted, let's say, if they don't vary as much, then if you do have a difference between the groups, right, between, let's say, males and females, you're more likely to find it if their scores don't vary a lot, right? So women all score a certain way, men all score a certain way, let's say, and you can clearly see that there's a difference. Assuming that, that you expect that difference, for instance, that such a difference is actually real, okay? You're not gonna find that difference, okay, if it's just something that, doesn't exist, okay? So, but what I'm saying is, if in the population there is a real difference, let's say, between men and women in how much alcohol they consume, let's say, the number of alcoholic drinks they consume, if when you survey people and you ask them about this stuff, let's say, and you compare men and women, you're more likely to find that difference, right? A real difference if there's not a lot of variation. So for instance, all the women say they have between 2 or 3 drinks a week. Some of them said 1, 2, 3, but most it's small, right? And most men said they have 5, 7, 6, 8, right? Most men, their scores are all similar too, but they're higher, right? There's a real difference here and you can easily see it, okay? So variance really has to do with variation. The more variation, the harder it is to see the difference. The less variation, the easier to see a difference. And that's it, you guys. Let me stop recording here.